Welcome back to Advent of Code 2019, day 18. Hello, DJ. So today is a non-int code problem. It seems every odd-numbered day is int code, which was yesterday. Today, this one looks like some sort of searching, pathfinding, shortest path algorithm. It looks like a traveling salesman problem, which is NP hard, but okay, so man, I was so excited for int code. Yesterday's I solved by hand. I solved part 2 by hand, which is strange. Well, at least most of it by hand. Running the int code problem obviously needed to be done programmatically, but yeah, it felt like it would be quicker to solve by hand than to actually write a program to solve it in this particular instance. Okay. 18. Many worlds interpretation. Oh, I forgot to put the kettle on, and if I put the kettle on now, it's going to be really noisy. Unless I put kettle somewhere else. Let's read a bit of this first. As you approach Neptune. Okay, so we've arrived at Neptune. So, from what I understand, these planets are... Well, one of them is not a planet. So we've got Mercury, Venus, Earth, Mars. And then this one is the Ceres monitoring station, apparently, which seems to also be orbiting the sun. But then everything else after that, it's Mars, Jupiter, Saturn, Uranus, Neptune. So we're on to Neptune now. And then I guess Pluto is off in the distance there. If we count it as a planet, I can't keep track of whether it is or isn't a planet at this point. All right. I think it's now not a planet. As you approach Neptune, a planetary security system detects you and activates a giant tractor beam on Triton. You have no choice but to land. A scan of the local area reveals only one interesting feature, a massive underground vault. You generate a map of the tunnels, your puzzle input. The tunnels are too narrow to move diagonally. Okay. I can deal with that. Only one entrance, marked ampersand, is present among the open passages, marked dot, and stone walls. Yeah, sure. But you also detect an assortment of keys, shown as lowercase letters, and doors, shown as uppercase letters. Oh my god, is it one big keys and doors puzzle? Is this like some sort of Legend of Zelda type algorithm? So we enter in the center here. So I'm guessing we have to find the corresponding small letters for the large letters. Okay. Interesting. It's some sort of breadth first search, except your nodes are not individual cells in the map, but your nodes are actually keys and doors. So you're kind of, instead of deciding whether to go up, left, down, or right, you're deciding which key do I go for next, or which door do I go for next. So all your keys are neighbors, or at least the accessible ones are, and all your doors for which you have a key are also neighbors. So then it's that sort of breadth first search, a different kind of breadth first search. And there's an inner breadth first search you would need to do to find the shortest distance to the doors and keys as well. I'm getting ahead of myself though. That might not be what we're trying to do. Keys, yeah. Okay. You aren't sure which key you need to disable the tractor beams, so you'll need to collect all of them. That makes it easier. Then I know I need to collect all of them. I don't need to decide which ones to discard or whatever. Starting from the entrance, you can only access a large door, A, and a key. So the goal... Oh, the goal is to collect every key. Interesting. How many steps is the shortest path that collects all of the keys? Interesting problem. But I think what I said earlier is the right approach. Just a breadth first search. Like a double layered breadth first search. Interesting. Is it? It's not a tree, is it? It's... Are there loops? Well, there are loops. Well, there's at least one loop here. Hello, Flynn. Yeah, back on the AOC. It looks mostly like it's a tree, i.e. there's no cycles, which will make it way, way easier. It might not be. I mean, not that it matters. We write the algorithm similarly. So at every kind of phase, we want to make a beeline straight for either a key or a door that we hold the key for. Wait, no. We don't even want to head for a door. Why are we heading for a door? Every step, we only choose a key which is accessible. So any key that's locked behind a door that we don't have a key for, that's an inaccessible key. So we do a flood fill, basically, to work out which keys are accessible, taking into account which keys we're holding. And then the outer breadth first search will be choosing each of those as possible neighbors to go to. So it's not quite like a traveling salesman. Well, it is sort of, but... It's kind of... It is a traveling salesman problem, but it's in a sort of tree, or a very tree-ish map, which would mean it would no longer be MP complete. Kind of. And this here is sort of a cycle, but you can this 3x3 space in the middle, you can compress it down to be a single node in theory. So it's technically a cycle, but not really. You can contract it. I don't think there are cycles here. It's hard to tell. But it looks like it's a very low cycle count anyway, so that would imply that it's a tree, in which case it would be polynomial. Yeah, and so you would just use pathfinding as normal. Interesting. Okay. So there are how many keys? It looks like there's one for every letter of the alphabet, so 26. So there's 20. Breadth is 26. We're trying to find the shortest path. But the state space is the tricky one, because you could have 2 to the power of 26 different assortments of keys in your inventory. It's actually strictly harder than Traveling Salesman on a tree, because they put doors in the way. So there's like a wide range of possible assortments of keys you're carrying. So the state space is where you're standing combined with what keys you're carrying. Now, even though there are so many possibilities there, like so it would basically be 26 times 2 to the power of 26. So it's that many possible states. So it's like 2 trillion. But I don't think we'll realize all of those states anyway, so... I'm guessing the doors are sort of forcing a topological order here, so that most of those states are not possible. Like, you can't have the late keys without having the earlier keys. So I think it will just work. If we just run breadth first search, it might just work. Well, we'll run it. I mean, if it doesn't, then what? Maybe we have to look to some sort of topological ordering, like work out which keys must be accessed before other keys. But I don't think we would need to do that. This is a part 1, so it shouldn't actually be that difficult. We'll see. I mean, if we weren't doing it, the brute force C type approach would be try all possible orders of keys, of which there are 26 factorial. Which is too many, of course. But yeah, all right. Breadth first search then. It looks like they've sort of placed doors in places that would mean at any stage you can only get like 2 or 3 keys, maybe, or something else, something like that. All right. Let me just put the kettle on. So have you been doing? I can't remember what you said, Flynn, before. You've been doing 2019 or a different year? Also, I have a leaderboard. I haven't checked it in a while. I did several... I'm using a new chat tool and I can't scroll down in it for some reason. I did several rewrites of this. From first opus. Ah, okay, you are on the leaderboard. Oh yeah, I did notice that these two popped up recently. So Yeah. Cool. Alright. Let me put the kettle on, and I'm also trying to... sort out the chat window there. I think that's fine. Okay. I'll leave the description up. I have to go find a socket somewhere so that the kettle won't be loud on stream. All right, so still pretty loud, but all right. 18. The input. I've had so much practice with these 2D grids, so I'm starting to get the hang of them. Alright, so we put the raw string in each row of the grid. Should we wrap this up as a class? Because we'll want like a shortest path method or something. Should we do this in the constructor? That's probably not advisable in Python, but I don't see any reason why not. This is wrong. It should be... Okay, we'll sort that out. Self.grid equals that. For line in f.relines. Grid.append line.strip self.grid. Right. So want to record some locations, I guess. Just like a map of all We don't care about where the doors are. The doors just happen to be there when we're traversing the graph. We do care about where the keys are, because those are our nodes that we're actually heading to. The doors are mostly irrelevant unless we happen to walk into them. Right, so during this process, probably want to let's copy some vector class that we used before. So on the even numbers, probably are when did I use a vector? Well, that was like a 4D vector, 3D vector. No, we didn't do it there. I can't remember. Pos. It was pos. Oh no, that was just a raw tuple. I'm sure there was some place where we had vector defined with addition and all that. We'll just go through each of them one by one. No. Oh, it was asteroids one, maybe further back. Should I just write it from scratch? Yeah, but this is the asteroids one, but this is not what I was thinking of. Okay, we'll just write it from scratch. Okay, so we want a call it a pause. Let's make it a data class. This is a really cool new thing in Python. I say new, but it's been around for ages now. But so no, we want rows and columns. Yeah, rows and columns. So row. No, I's and J's. That kind of means rows and columns, but I's and J's. All right. Okay. Data classes. No, we just data class, right? We just. Oh yeah. From data. Okay, just leave it like that for now. So as we're going through this grid, we want to find all the relevant things. So keys. Let's call it. Just make a hash map. So for each small letter, so we're saying or. So it'll be for the J. So it'll be, let's say, for I, line in enumerate read lines. So that'll get the row for j r in enumerate line dot strip. If dot l dot is other string methods to see if something's a lowercase. Or you could say is if dot lower equals. Let's just check if Python check if character is lowercase. Is alpha. Oh, there's an is lower. Okay. Is lower. But you also need to check is alpha because it will probably return true on other symbols. So we want self.keys. So it's going to be pos ij. So the character is mapped to pos. I was just going to ask about that. I checked both. Yeah, I think you do need to check both because it's designed for using with sentences and natural language. So all the commas and full stops and everything is going to just return true vacuously for them. Let me grab my coffee as well. Alright, so we've stored the keys. Elif equals ampersand. We will probably want just keep track of what we're actually storing here. Self dot start. Anything else? That should be it. Doors we don't worry about. Okay. Okay. So we probably want some methods here, like for example, is walkable. Define is walkable, or define get pos turn self.grid pos 0 pos 1 define is walkable is not equal to hash. Because there's walls around the outside, you can never actually end up being out of bounds. So we don't even really need to do out of bounds checks. It would be good practice to do it anyway, but... nah, because our neighbor method is going to be walkable neighbors, so we don't really need to do that. Get neighbors then. Define get neighbors of a given pos. For delta in, so it'll be zero, pos -1, 0, pos 0, -1, pos 0, 1. Well, we don't have an addition. We should really do that now. Okay. Subtraction? I don't think we'll even use subtraction. Hash and equality we get for free because of data class. Anything else? Distance? No, we don't even need distance. We're not using A* search or anything like that. I think that's fine. Neighbor equals pos plus delta. If is walkable or neighbor, self dot is walkable. Yield neighbor. So that yields all the walkable neighbors. Okay, so far so good. Nice and clean. What else? I'm gonna have to... Hello, original Bugle. What is yield? Yield lets you treat your function as a generator in Python. So if I were to... I don't really want to return a final value and finish the algorithm. Instead, I just want to sort of return things as I compute them. So if I were to now do this for neighbor in get neighbors, right? Well, get neighbors of a pos or whatever. It would start running get neighbors, but the moment it hits yield, it will return that one value, and that will come out of the generator, and then it will stop. It will pause computation until you request the next one. So then in this inner loop, we'll just do whatever we want with that neighbor. And then the moment we want a new one, we'll then carry on computation. So it's like, it's just lazy evaluation sort of. It's only doing as much work as it needs to get to the next neighbor and so on. So we'll fetch ech neighbor, I mean, the end result is the same in this particular case because it's not exactly a very high computation method, but it's just nice and efficient because now we don't need to make a list, because normally you would do this. You would say neighbors equals list. You would say neighbors.append neighbor, and then afterwards at the end you would have return neighbors, and then this down here would still work, right? Because you've got a list instead of a generator. But if you wrap everything up as generators, it's just kind of nice and efficient, and then you have some optimizations and all this stuff. And it's fewer lines of code as well, because now I don't need to explicitly create this thing. It's just yielding whatever it's computed at the time that it's computed. But you can do nice things with this. You can make infinite generators, and you never worry about getting into an infinite loop, because you could just say like you could just have an iterator that increases from 1, 2, 3, 4 and yield each of those, and basically you've created an infinite generator which gets a new ID number. That's a good example, actually, creating ID numbers, because you want to always get the next available ID number that no one's using yet, so you just increment a counter. And that's an infinite method, but you'll never have infinite computation because it's like it only computes the next ID number when you need it. So you can do some cool things with generators. It's one of the very Pythonic things which thought I understood yield soon after I first encountered it, but still trying to wrap my head around generators, especially the way the Encode implementation works with it. Yeah, the Encode, the way that I've done Encode, there's still a couple of things that I don't fully understand why they work, but they do work. But yeah, I mean, it's a quite complex thing, and it's similar to like stuff that you do when you study functional languages like Haskell and stuff, treating everything as a function and yeah, I mean, those basic examples are you can do a lot with those examples I've just described. And like if I actually want to finish explicitly, I can say return, but you don't need that. But you may want to return under certain conditions, so it will automatically like stop once there's no more neighbors in this particular example. But yeah, I try to wrap everything up as these generators because it's a bit cleaner. You just have to remember that what you get neighbors will return a generator. So it's not like you can do length off get neighbors or anything like that. You do need to fetch the neighbors, but you can do like list, cast it to a list if you wanted it as a list. And if you wanted to sort that list, then you could then sort that list and so on. I mean, you could do this. Sorted get neighbors. Oops. Now, I think in order to do that, it would actually have to compute all the neighbors behind the scenes, and then it will return them in a sorted order, I guess. It also avoids having lots of kind of like variables, like lists floating around, which then have to be deconstructed later. Initially explicitly saved the state when it was supposed to get input, but then realized that the yield just pauses without doing that because of the generator aspect. Yeah. Yeah, I think the Python's yield made the whole Encode implementation very interesting. It must have been a lot harder to do it in the Encode stuff in C++, managing this concurrency type thing that we're trying to do with inputs and outputs. Thanks for the follow, Original Boogle. Are you doing Advent of Code yourself? Or have you done any in the past? Alright, so I think those are all the helper methods we want. From Q, we'll need a Q. The breadth first search. So we've got the start location and the doors. Oh, we could have a helper method to deal with doors. Or just check that in the BFS. We can just say, define needs key. A given pause, well, it is the Boolean expression saying whether we need a key to access this particular spot. So, and it returns let's say required key. So it's telling us what key is required to access this spot, or none if no key is needed. So let's say if so we're saying if it's upper, if get neighbors what is the goal about your program? If you can explain easy, please, because I don't speak very good English. All right, so let me also post the link for the site. I don't know if you've seen it. Hang on. So that link is the problem I'm trying to solve. It's a puzzle, basically. And the general gist of it, the simple explanation, is that we have a map, we have small letters, which are keys, and we have big letters, which are doors. So a small letter C, if we pick up that key, it's like in a video game. If we pick up that key, we're now allowed to open the big door, C. And if we pick up E, we're allowed to open big E. So we start at the ampersand, which is the middle here, and we have to collect every key, but we can't get through doors unless we have the corresponding key. So you have to figure out the shortest path to open, collecting all the keys. So it's like you might go to B first, then unlock, pick up G, unlock B, pick up N. I don't know. Something like that. You have to work out the shortest path to collect all the keys. Just say equals that. So car dot is alpha and it's upper. Oh, why get neighbors? No, get pause. There we go. So if it's an upper, then we basically return car dot lower. Turn none. Okay, so that's just telling us the required key, if any, to access this spot. I think we've got everything now. I love data class. Okay, so... So we're saying a state is the combination of position I'm standing in and a hash set of the keys that I'm carrying, so that its order doesn't matter. And because this is a data class, it already knows how to hash positions. Wait, hash... No. Well, a hash set itself would need to be... Thanks for introducing me to data class. I was having trouble learning the base Python class. Data class simplifies a bunch of stuff. Yeah, it does. And it's been around for a while, but I only started using it, I think, last year. I knew about it in the past, but I just kind of kept putting it off. But yeah, it's just... I mean, when I worked at a company, so many times, it's just the same thing over and over again. You write a class, and then you have to spend ages listing all the variables and the... and then in the constructor having to set this to this, this to this, this to this. It just takes away all that, plus gives you the obvious equality check, the hash check, which you can override if you have a more complex logic. But yeah, it's just, there's so many easy classes you make where you don't, it's the obvious approach just works, like testing the equality of the 3 parameters or whatever for a 3 integer vector. But yeah, it's good. I'll go to eat my breakfast, but it is a good stream soon, thanks. Alright, thank you, Original Bugle. Over the next few days I'll try to do more of these Advent of Code problems, because I'm trying to get this done. But yeah, in the case of this data class, we can also make it frozen, which in this case makes sense. So let's do that. That means it's like, it is a immutable vector. So you're not allowed to change IOJ. That means it's hashable now. I think if I didn't do this, it wouldn't be hashable. So I actually do have to do that. Gotta just marathon the last couple days. I don't know how hard they'll be. The last day is usually not too hard because it's Christmas Day. I'm sure that Eric is well aware that he is depriving us of our families, because we will spend the whole day solving Advent of Code if we need to. Not that I ever really spend Christmas with my family. I'm usually halfway around the world from them, but yeah. We'll see how hard it gets for this year. Will it be an ink code problem? Hang on, so it's what? It's odd numbers. So it could be an ink code. Yeah, it probably will be. Alright, so let me... Alright, let's run this because... Yep, no crashing. Okay. I'm really enjoying the ink code stuff. Yeah, this was definitely a very unique year. I don't think he's done this again. Like, I haven't seen 2020, but I can imagine a lot of people didn't like it. It's a very polarizing thing. Some people don't like the fact that if they get stuck on the initial encode problems, then they wouldn't be able to solve any of the remaining ones. I get that. That would be quite demotivating if someone's, you know, a beginner and they... Programming the encode is not exactly easy, and I can see a lot of people getting stuck on that, and then that kind of locks them out from half the problems in the whole month. Especially that concurrency thing, like dealing with the inputs and outputs. Like, that's not beginner level stuff for coding. That's pretty advanced. So yeah, I can see it being polarizing, and that's probably why he's just not done it again. Nevertheless, it was an interesting thing to have for this particular year. More funding than the assembly stuff. Yeah, I mean, yeah, exactly. Once you've got the assembly stuff out of the way, which again is kind of complicated, but then it's nice that you've actually got this little computer which is actually interactable. Like, you're actually giving it inputs, it's giving you outputs, it's literally running a robot pathfinding algorithm behind the scenes and telling you what the map looks like. It was literally running a game of Breakout with the ball bouncing up and down and moving the paddle and stuff. This is, I've never seen anything, any coding challenge like this. So it was really quite clever. And you would never be able to do a challenge like that if you didn't continuously build it up over several days. I'm amazed at what they've coded in that. Yeah, exactly. He spent a long time putting that together, I'm guessing. And you could probably... Python has some libraries where you could make an animation, so you could actually see the ball and the paddle moving in place rather than just printing out every individual map. You could actually just have the game, you know, running. Maybe I should look into that for next time, because there are several problems which you probably want to run an animation for. Seeing things move about. In fact, that's a great visualization tool. I should actually prepare that for next year's thing. But yeah, cool challenge. As I understand it, Eric is kind of into that stuff because before Advent of Code, he made some kind of challenges, but they were a bit more on the assembly type side of things. And back then it wasn't majorly popular, so it was just a few of his colleagues and stuff that he was sharing it with. I can't remember what it was called. It's still on GitHub, but it's very difficult to get it working again because there's no longer a server for it, so you have to run your own server to make it work. But it is some sort of coding challenge which involves a similar thing, creating a computer and running it and doing stuff. I think it's was it the Cinecore challenge? He actually, because Eric worked for, I think, the company called Cinecore, so he actually made it as a tool for, I don't know, maybe interviewing new applicants to actually join the company. So he actually, maybe that was what it was for. Alright, let's actually do this BFS then. So given a start location, which we'll get from the grid, so the initial... Alright, let's make a helper method here. Define get state. So given a position and a hash set of keys, because you can't hash a set of keys. If you try to hash a set of keys, you'll just take the memory location of that set, which won't work. So we need to actually take out the keys, put them into a sorted string, and hash that string, or a sorted tuple. Let's go with string. So key string equals, so we're going to take, so we want to join up all the keys, but we want sorted. I think that'll work. So sorted is another generator. It's going to take the keys in sorted order, and you can just apply this to join them up as one string. So if you do that, then you should just be able to do this. Return the tuple, pos key string. I mean, we could just simplify this. So if we do that, then we should be able to say, initial state equals get state start just an empty set because we hold no keys. So of course we need a queue. Put the initial state in the queue. So we're gonna have to make two passes of this. Well, there's an inner breadth first search we need to do, because we need to actually do a flood fill to see where we can get to in the first place, sort of. Would this be too expensive though? Like if we did an initial all paths, shortest path algorithm, that will get us the distance between every pair of points, but it doesn't take doors into account. And if there are cycles, it's not taking into account that although it would require a door to get from A to B, a key to get from A to B, there may be another path that goes around which doesn't need that, and that is not stored in that knowledge. But then the map kind of looks like a tree, in which case, is the set hashable, or does it need to be a tuple? Technically it is hashable, but the result is not what you want it to be. It's just going to take the memory location where the set is stored, I think. Actually, no. I think it will just complain. I think it will just error. So, yeah, I think it will just error. It will say this is immutable. This is not immutable, so you can't hash it. It needs to be a tuple, yeah, or string, or any immutable thing. had a terrible time turning lists into sets, tuples, whatever, to make that part work. Really? What was the issue you were having? Because, I mean, in the general case, it should just be... sort the list, and then put tuple in front of it, but still learning what is hashable. Yeah, I mean, that's a pretty complex topic, and the most important thing is that it's unique and that order doesn't matter. So if I have keys A and B, and in another instance I had keys B and A, you want those two to be the same. So yeah, if you sort the list, it will always be AB, and then it actually can see that then AB and BA will map to the same bucket. So sorting is one way to get around it, but there's other ways. So I'm trying to think now whether I should be doing... Is this actually a tree? I think this actually makes a difference, whether it's a tree or not. I mean, apart from this center... How do you test if something is a tree? You run... Well, you run BFS, don't you? That's... BFS is a cycle finding... Oh, it's not a tree. I can see. There is a loop. Yeah, it's... Hang on. Or maybe my eyes deceive me, I don't know. It's really hard to tell. Yeah, so if I ran BFS, I could probably tell whether it's a tree. We just have to ignore this center, because clearly that's a cycle. But we don't care about that cycle, because it's like... not a big deal, but... in other places it would be a big deal. Because my worry is, if I keep doing a flood fill between every step, that's gonna be a lot of work. I could try doing it, and if it doesn't work, then we just do some sort of smart tree approach. Like, so I'm standing here. I do a flood fill to see where I can reach. Now that takes kind of like linear time. Well, quadratic time, linear time in terms of how much stuff is in the map, of which there is like almost 100 by 100 almost, so it's like 10,000. So that's a 10,000 step operation to find all the keys I can access. Then I choose which neighbor to go to. So the outer BFS is linear in terms of the number of keys, I guess. Well, yeah. Well, not quite, because states, a node is keys plus this hash set. So it's basically 10,000 times some indeterminate number of possible states, which could be big. Alright. We'll just try the slow approach. let's say we need a helper method here. Define get reachable keys from a given starting position and a set of keys we're holding. Right, so that will mean we can access doors and stuff like this. So this is going to run BFS and take however long it takes. So it's basically this again, but the state now is just position. We don't care about state key. Number of keys we're holding is not going to change because we just move to the one key and then stop there. So it's sort of like it's just we want a distance table. But once we do this, this is no longer BFS. This is Dijkstra. Because it's not unit distance to each key. Different distances to each key. So that means we can't use Q. We need to also import priority queue and use that. Alright, well, we'll need to figure this out later. Let's try and do the get reachable keys thing. Right. While not q.empty. Get the next item from the queue. Alright, so the next item on the queue is a neighbor that we found previously and added to the queue. If Alright, so if this is a key, then we're gonna let's rename this to held keys. And we want to say just make map called keys, because this is going to actually tell us how far each key is. If let's just make another method. Is key. Define is key. Something like this. If self dot is key, keys so it'll be self dot, yeah, just get the character equals dist, the shortest distance, and then we don't take any neighbors from this, because the point is we don't ever want to go further than that key, because in the outer Dijkstra I've changed from using Q to DQ, double-ender Q in these puzzles. DQ is easier to use in some ways, just make sure which end you're getting from. Main advantage of Q seems to be locking for threading. Yeah, I was thinking about that, because I never really touched DQ much, but clearly, so Q is a wrapper around DQ, isn't it? There's no, and DQ actually offers a couple more methods that Q doesn't have, I think. I could, you can say while Q. Yeah, let's try doing that. I mean, unless I need something specific from Q, there's what's it called? Is it just... Oh, it's not. It's not. It... Ah, it's collections. Okay, we'll try using DQ, yeah. I actually probably should use it most of the times, because we don't... never doing any threading or anything like this. Ah, so you treat it... it looks like a list then, yeah, that makes sense. Append and pop left. So pop will be like the stack and pop left will be the... Okay, that's cool. If it's a key, we now just continue on to the next item from the queue, because we only want the immediate keys and nothing beyond them. So, if it's a door, if self.required key of current not in held keys. Continue. We can't get past this door. And we don't expand any nodes from there. We can't stand on the door, even. So, aside from these two situations, we would just expand neighbors as normal. So, for neighbor in get neighbors, if neighbor in dist, so that means we've already put it in dist, that means we've already treated it as put it in the queue before, so skip this. Get neighbors. Get neighbors is specifically walkable neighbors, yeah. So then dist neighbor equals dist current plus 1 q dot append neighbor. Is it as simple as that? Nothing, no other checks needed? So we stop until we've hit keys in every possible path, or just like dead end or whatever. And then turn the mapping so we got all the keys and distances. So we can test this. Let's test this just by getting the reachable keys from start. Okay, so we start with an empty set, holding no keys. I missed something. Do you still have a breadth first search or Dijkstra? Well, breadth first search is what I'm using to find all the reachable keys from where I'm standing. And Dijkstra is sort of the outer layer, so that's using the knowledge of how far each key is from us. We treat those as nodes that we can go to. And in each step, we would get reachable keys again from when we're standing, which might be too much work, but we can try that to begin with. So I'm using both, basically. In each step of Dijkstra, I rerun breadth first search to find all the keys I can get to. Get pause. Return. So, oh yeah, of course. This is pause. I pause. J. Yay, we got nothing. Okay, it's broken. Oh! This check is redundant. We need to say if self.required key current is not none and okay, because none is not in the keys list, so this is always failing. All right, do that again. There we go. So we've got H at distance 10, E at distance 32. Okay, that looks very believable. I mean, we can test that on one of the easier examples. Just make sure it's actually correct. So I'll paste in... Okay, I like the look of this one. A, G, B, F, D, H, C, E. That sounds like a lot. Oh, no, that does look about right. Hang on, so A, 1, 2, 3. Definitely use the examples on this day. Actual input is a B, C, yeah. G, 3, B, 3, F, 3, D, 1, 2, 3, 4, 5. H5, C5, E5. Okay, it's quite symmetric, but yeah, clearly we can't get past B. So now we can change it. So we can say if we're holding key A, so now we're holding A. So that unlocks... Ah, no, because B is the next... Oh, damn, hang on. Yeah, there's an issue, yeah. Ah. No. No, that's not an issue. B would still be... Yeah, B would still be where we stop. That's correct. But... if we held key B... if we happen to be holding key B, okay, let's try this one. So this one I think will have an issue. If we're holding A and B, it's the same. Okay, but it's not what we want. If we're holding A and B, we do want J to be the next key, not B. So basically, we want to skip over any keys that we're already holding, because that's not a reachable key anymore under our semantic meaning of this method. J would be the next one. So we want to say if, so where we said if it's a key, and self dot get pause current not in held keys, then we would treat this as if it's just empty space. if we had it in held keys, then we would just treat it as if it's empty space. Let's try that now. Yes, so we don't get B or A, because we're holding A and B already. J is the next reachable one. Perfect. 1, 2, 3, 4, 5, 6, 7, 8. Okay, are there any other tricky twists? I don't think so. So if I held A, B, C, D, E, F, G, H, so we could just say set of A, B, C, D, E, F, G, H, K, N, J, O, L, M, I, P. That looks pretty good. Okay. So that's step one. Next step is now to implement Dijkstra. We'll continue with this basic example here. So, get state, empty set. Okay. So Q equals priority queue. So we need dist equals a hash map. Initial state goes to 0. Q dot put. So we want to put the item. So the state and the priority, which would be, it would be 0, but let's just be precise about how we're computing that. The dist to that initial state. Wait, what? Oh, you have to put it in as a tuple. Yeah, you don't give priority as a separate parameter. Okay, so put the dist as the first parameter. Of the tuple. Make sure this runs. Okay. So while not q dot empty. Okay. So Okay, so we want to... Man, this is harder to think of. Dijkstra is always a little bit harder to think about than BFS, but in principle, it's just... You're just substituting the priority in. So, okay, so we want... I don't think we care what the priority is right now. Actually, we kind of do. So distance current equals q.get. Now, if d happens to be bigger than what we're currently storing in dist. No, wait. Yeah. If, because the priority queue doesn't have an easy way to delete redundant stuff. If we found a faster route to something, we would just put that new thing in and the old thing would still be in there. So if D is bigger than current is a state, then the distance to this state. That means at some point we put this in with this priority, but then we later found a better route. I'm guessing that probably won't happen because of the tree-like nature of this, but if that did happen, we would actually just discard this. Lazy deletion. We only want the one where that is actually the fastest known distance to that location. Okay, so we have, and now we don't care about what D is. So current state, so we can unpack current pos, current keys equals current. We need to do a goal check. If we need to know how many keys there are. It's not up A to Z, is it? Well, it's not, because in these test examples it's not. So we need to actually make a count here. So keys, we store them here. So we actually want a goal. And goal can just be a number of keys. So grid.start length of grid.keys. If length of current keys wait Where do we stop? We stop when we picked up the last key. So we've arrived at a key that we don't have. And our current, and so that makes our total plus 1 for the one that we're standing on is goal. That's when we stop. Count the keys from the input. When you have all of them, you're done. Yeah. So we're storing that basically as this parameter here. So if length of current keys plus 1 equals goal, because in every step of this we've actually moved to a new key, except for the initial state, I guess. But that's fine. I mean, we could be extremely accurate here. So we could say, if let's say, if grid dot is key current pos. So basically we've moved to a key which we don't have, because by definition that's what we did with this BFS. And length of current keys plus 1 is the goal, then we're done. What do we return? The distance. Return D. The distance. Or just say return dist current. Let's do that. No. When we put this in the queue, we'll have added this key in. No, we won't have. Will we? Hang on. I think, distance. Yeah, no. The moment we're standing here, it's as if this key doesn't exist on the map anymore. This is wrong. This will actually be in current keys. So we just have to say if length of current keys equals goal. The moment this comes out of the queue, it's as if we now have that key and it's no longer on the map. Yeah. So basically, the number of steps it took to get to this place where we're holding all keys. Okay, so that's the goal check. So ideally, we should never exhaust this queue. Unless something went wrong. So, with this goal check out of the way, we don't have all keys. So it should always be possible to find new reachable keys. Unless the doors are in soft lock places, so that should, we're assuming that wouldn't happen. So now we can run the BFS. So, reachable keys equals grid.get reachable keys from current pos current keys. So that'll get a map of keys. And it's taking us to all reachable keys that are not already held. So these are all guaranteed to be neighbors, new neighbors that make sense to go to. So for key running out of variable names, just say path distance in reachable keys dot items. So for No. Location. Or pos, whatever. Yeah, it's giving us the location of them. No, it's not. What is it doing? Keys equals... distance. Wait, what do we want? Oh... we actually want both the location and the distance. We don't know... yeah, this needs to work out both of those things. So we should actually say keys equals current and distance to current. For key... hello, Gun Voidwalker. No idea what's going on. I'm just happy to be a part of it. Do you do any coding in Python? And do you... oh, thank you for the follow, by the way. Have you ever looked at Advent of Code before? This website that I'm using. Running out of variable names. I have so many warnings about having multiple variable names, yeah. Couple of thousand of hours of Python. So can I just do this? Just say pause path distance. Can I even do this? Can I unpack them this way? I can't remember. We'll try. So... we need to work out what the new state will be. So the new position, neighbor pos equals, well, that is just that. Neighbor the new set of keys. What are we calling it? Just keys. Let's call it held keys. Just be very clear here. If that works, that's a new Python thing to me. I don't even know. We'll find out. Neighbor held keys equals so it'll be current keys. We should say current held keys union just this one new key. So that will create a new set without modifying the current set. So neighbor state, we'll just say neighbor equals get state. So it'll be neighbor pos neighbor, and we can just do this. So that is the neighbor state. The neighbor distance equals dist to current plus path distance. So we now have a neighbor and a distance to said neighbor. We should do the check. So if it's already in dist. So if neighbor in dist and dist neighbor is actually less than what we found here, then this is redundant. We've already found a better path before. I mean, if it's less than or equal to, because if it's less than or equal to, that means we found this distance before. So right now we found a better distance to this neighbor than infinite if we never found a distance to this neighbor before. Oh man, this is getting hard to keep track of. So now we want to actually put it in the dist table. So dist neighbor equals neighbor distance, and then q dot put. So it's going to be so in Dijkstra you just put the full distance, don't you? So it's going to be neighbor distance neighbor. Yeah. Alright, that was a mouthful. There's many ways this could go wrong. Neighbor using the state. Okay. If we somehow get here, we want to say print, I don't know, error. Goal not reached. So we're returning the distance, the shortest distance to getting all keys. So ultimately it should just be whatever value this spits out. Okay. Run. String and set. Current held keys is a string? Ah, of course it is, because we wanted it to be hashable. So just say key string equals current. We need to make a set out of that. Like the best way, the cleanest way to do it really would be to create a custom class for a hashable class of keys, but we can just keep going back and forth with this. We can say this equals set of key string. Pos needs less than defined. And now, oh, 136. That's for this. Is that actually the answer? No. Yes, it is 136. Right, should we just test all the examples first? We'll just test the examples at the end. So there was this one. So this should be 132. 132. Now, it took a while for that big example, so I'm worried that the whole thing will actually just take forever. But, I mean, at least we've got a sort of correct answer for the examples. So this should be 80. This one should be 81. Okay. Oh, man. Now. Oh man, this is huge. It's not gonna run, is it? We need something better. Try running it. I do want to see what kind of progress we're making though. So can we say can we print out max keys equal 0. Say if hang on. Yeah, so if length current keys is greater than max keys, max keys equals that, print max keys. I want to see how many keys we get to. Also, how many keys are we expecting? Alright, start again. 26 keys, okay. 7, 8. Now it's slowing down. I mean, that's halfway through the keys. But yeah, running this shortest path algorithm every time, that's the step we need to cut out somehow. It's still climbing though. So now the question, we can use BFS to work out if this is a tree or not. That's an application of BFS. We just want to ignore this cycle at the start. Is this the actual input? Yes. I'm running it on the actual input, yeah. So we're trying to get to 26 keys. We're getting as far as 12. It's climbing, so might get there, but I feel like we need an all nodes shortest path algorithm here, so that we don't need to keep calling BFS. But yeah. We just need to ignore this bit here. I mean, I could just assume it's a tree because it looks like a tree, so we could just run it as if it was a tree. In which case, what I do is I use Floyd-Warshall's... I mean, it's still climbing at a reasonable pace, so Floyd-Warshall's all shortest path algorithm to find the shortest path between every pair of points. And not only is it shortest path, but it is the only path. There's only one path between every pair of points if it's a tree. I mean, apart from this middle section, as I said before. And you would have to qualify each of these paths, not only with the distance, but all the doors that are in the way, I suppose. Then, every time we're doing BFS, instead of doing BFS, we'll just call up our Floyd-Warshall table, which we pre-computed in like cubic time, so that's... It's still going to take a long time, isn't it? It's cubic in... Well, let me look this up again. Floyd-Warshall algorithm. Yeah, it's cubic in the number of nodes. How many nodes do we have here? It's something like 80 times 80 over 2, because like, I don't know, like roughly half of these are walkable nodes, so it's going to be 80 times 80 over 2, which is 3,200, so 3,200 cubed. That's still quite a lot, isn't it? 3,200. So the 3. Yeah, that's too much. But it's a tree. So it actually shouldn't take that long. We can actually... We don't need to use Floyd-Warshalls. There is actually, you root the tree, and then the path is right there in front of us. You go to the root of the tree, and then for part 1, I initially had 3 searches. You seem to have 2. I eventually rewrote it to just have 1. Still takes about 5 seconds, which seems long for a part 1. 3 searches. Interesting. Oh, we're up to 20. Oh, wow. We're actually going to finish. Okay. Because this... I think the key to this is using it as a tree, in which case the path from any node to any other node is completely known once you know the tree structure. You just find the... lowest common ancestor of both nodes, and you take the distance to that ancestor and then the distance from that ancestor to the other node. That's the algorithm. So once you know the tree, in constant time, basically you can find the path and the distance. But that means coding up a tree and everything. It looks like we'll actually finish. Even though this is a crazy long time, but it's not completely unreasonable amount of time. But yeah, once you use... I'm guessing for part 2 we will actually have to go to a tree implementation. And we could just say the root is the union of these 9 squares in the middle. Sort of. Well... Oh. Not quite. That's not quite correct. We can figure something out with that. But, oh, if it's the wrong answer, I'm going to be a bit disappointed, though, because this is working on all the test examples. I am printing the result correctly, aren't I? I hope so. We're returning the distance to current, number of steps, until we're holding... Yeah, should be. But yeah, it's just like... Alright, there we go. 3, 2, 1, 6. Alright, I might not do part 1 this stream. Part 2 this stream. We'll just take a sneak peek at it. Correct. Took a while, but we got the correct answer. Let's read part 2 then. You arrive at the vault only to discover that there is not 1 vault, but 4, each with its own entrance. On your map, find the area in the middle that looks like this. Update your map to instead use the correct data. Like that. This change will split your map into 4 separate sections, each with its own entrance. Oh. This is interesting, because it's sort of splitting it this way makes it more of a tree than before. But now we've got 4 parallel robots. Okay, so because some of the keys are... It would take much too long to collect all the keys by yourself. Instead, you deploy 4 remote-controlled robots. Each starts at one of the entrances. Collect all of the keys in the fewest steps, but now each robot has its own position and can move independently. You can only remotely control a single robot at a time, so it's the sum of their steps. Okay, interesting. Collecting a key instantly unlocks any corresponding doors, regardless of the vault in which the key or door is found. My first thought is that it doesn't seem much harder than what we've done right now. But... yeah, no, it is, isn't it? Because your positions of the robots... You got 4 different positions of the robots as your states. But assuming I move to the tree implementation, you've now got a rooted tree from 4 different roots. So that will cut out the whole inner BFS. Alright, well anyway, lately I've been mainly doing it like I'll do part 1 in one stream and then do part 2 next time, which gives me a chance to actually think about it in the meantime, so my streams aren't as lengthy and less time spent just not getting any progress done. Hopefully. But so yeah, I'll think about this in the meantime. I mean, I say that, but I usually end up not doing, unless I go swimming. When I go swimming, that's like the prime time for me thinking about these problems. I just swim and I'm like, okay, I'll start mapping out algorithms in my head and stuff. I wasn't planning to go swimming today, but maybe I should. Ocean or pool? Pools. I always swim in pools. I often stay in beach towns, so I often see people swimming in the ocean, but I just think the ocean was not meant for humans. Like, I spent a lot of time in Thailand, and I saw so many people swimming in the sea, but there's deadly jellyfish there. There was literally, like, down the road from me, on an island I was living on, some kid died from a box jellyfish sting. Some Israeli kid, he was about 8 to 10 years old. But people just carry on swimming in the ocean. Like, it's deadly, it's kind of dirty because it is polluted from tourists and stuff. It's salty, you can get stung by jellyfish, you can stand on sharp rocks. Yeah, I always go to the pool only. Wait, what am I doing? I keep thinking about this problem. That there's time for that. All right. Well, yeah, pools are always clean. Well, as long as they keep it clean, but in general, it's cleaner than the sea. Yeah. All right. So let's close this down. So yeah, so next time I'll definitely have to switch to some sort of tree implementation as well. So that was, how long was that? 2 hours for part 1. Fine. Bit on the long side, but I might switch. Actually, because I'm planning okay, anyway. Thanks for watching. Yeah, I might, in 5-10 minutes, I might actually come back and stream a video game or something. I don't feel like killing some time before I go to the gym, so we'll see. Maybe Planet Crafter. Alright. Yeah, I might actually... I do want to get that game finished, because I am really curious about some stuff. Like, I want to look up all spoilers and routes and stuff, but I can't do that until I beat the game. So, yeah, I might actually come back with Planet Crafter in the next 10 minutes. I'll decide if I want to do that. So, yeah, if I do, then maybe see you then. Alright, thanks for watching. Bye-bye.